So, there's this chip, built in China, and according to the press releases, it's going to revolutionize everything. Again, every few months, some research lab announces they've built the chip that changes everything. Usually it's faster, sometimes it's smaller, occasionally it uses less power. Except, this time might actually be different. Because while everyone's been distracted by the latest AI drama, a team at Zhejiang University just quietly built something that makes our entire approach to AI look wasteful. Darwin 3. 235 million neurons on a single chip, clustered into a system called Darwin Monkey with 2 billion neurons total, running on 2,000 watts. For context, the GPUs training today's AI models burn through enough electricity to power small towns. This thing runs on less power than your microwave. It's architecturally superior. While we've been building bigger and more power-hungry AI systems, China just figured out how to build smarter ones. If you want to understand why this matters and why nobody's talking about it, hit subscribe, because this story goes deeper than you think. Most people think all computer chips are basically the same. They process information, they get hot, they make your laptop fan sound like a jet engine. But neuromorphic computing? See, your brain doesn't work like a computer. When you recognize your friend's face in a crowd, you're not systematically comparing facial measurements in a database. Your neurons fire in patterns, they spike when they need to communicate, and most importantly, they only use energy when they're actually doing something. Neuromorphic chips use spiking neural networks, artificial neurons that communicate by firing discrete electrical pulses, just like biological neurons. Only active neurons consume power. No activity, no energy waste. Think about it this way. Your brain runs on about 20 watts. That's less power than a light bulb. Meanwhile, the GPUs training today's AI models consume hundreds of thousands of watts. There's clearly a better way to do this. Building brain-like chips that actually work at scale? That's been the holy grail for decades. Companies have tried. Academics have published papers. Venture capital has been thrown around. And most of them ended up as expensive paperweights. So let's rewind to 2015. While everyone was losing their minds over the first iPhone with decent cameras, a team at Zhejiang University in China was working on something that seemed almost quaint by comparison. Darwin 1, their first neuromorphic chip. 2,048 neurons, 4 million synapses, built on ancient 180-nanometer technology. This wasn't about the destination. This was about proving the journey was even possible. Fast forward to 2019. Darwin 2 hits the scene with 150,000 neurons using 55-nanometer technology. That's roughly a 100x jump in just 4 years. Not bad. A honeybee has 1 million. Most Western companies were treating neuromorphic computing like a research curiosity. Intel had Loihi, IBM had True North. Academics published papers, and then what? Where was the systematic scaling? Where was the relentless iteration? Darwin 1 proved the concept. Darwin 2 added flexibility and real-world applications. Darwin 3? Darwin 3 was designed to win. See, most people think innovation happens in sudden breakthroughs, but that's not how real technological superiority gets built. It gets built through decade-long research programs with consistent funding and clear objectives. And while everyone else was chasing the next shiny thing, China was methodically solving neuromorphic computing. Now we get to the interesting part, because Darwin 3 isn't just bigger than its predecessors, it's architecturally completely different. Picture a 24 by 24 grid of computing nodes, organized into groups of 6 by 6, with each group containing 4 by 4 tiles. Each tile houses a neuron core and its router. It sounds simple until you realize what they actually built. A mesh network where every neuron can talk to every other neuron on the chip. The real breakthrough is their domain-specific instruction set architecture. 10 primary instructions, plus extensions, specifically designed for brain-inspired computing. Why does this matter? Because most neuromorphic chips before this were basically hardwired. You got whatever neuron model the designers baked in, and that was it. Darwin 3 is programmable. You can implement different neuron models, LIF, ISHIC, EVICH, whatever you need. You can program different learning rules right on the chip. STDP, reward modulated learning, custom plasticity rules. It's like the difference between a calculator and a computer. And then there's their connection compression system, which honestly might be the most underappreciated innovation here. They achieved up to 28.3 times better code density and improved fan-in and fan-out capabilities by 4,096 times and 3,072 times, respectively. What really sets Darwin 3 apart? The robust, on-chip learning capabilities. Most neuromorphic chips can only do inference. They're like a brain that can recognize patterns but can never learn new ones. Darwin 3 can adapt, update its weights, modify its behavior in real time. This all sounds great on paper, but how does it actually perform? Because we've seen plenty of chips that looked revolutionary in research papers and then disappeared into obscurity. Well, let's talk numbers. 2.35 million neurons per chip, around 100 million synapses. That's not just an incremental improvement. That's a different league entirely. But one chip doesn't make a supercomputer, so they built a cluster. 960 Darwin 3 chips networked together into something called Darwin Monkey, or Wukong, featuring over 2 billion neurons and more than 100 billion synapses. Now let's put this in context, because the comparisons are honestly brutal for everyone else. Intel's Hollow Point, previously the world's largest neuromorphic system, released in April 2024, 1.15 billion neurons. Respectable, right? A billion neurons is nothing to scoff at. Darwin Monkey? Over 2 billion neurons. China didn't just beat Intel's record, they nearly doubled it. Intel's Hollow Point consumes up to 2,600 watts at maximum load. Darwin Monkey? Around 2,000 watts for nearly twice the neural capacity. Let me break this down for you. China built a neuromorphic system that's almost twice as large as Intel's flagship, and it uses less power. That's not just engineering competence, that's architectural superiority. But raw numbers only tell part of the story. Because the real question isn't how many neurons you can cram onto silicon, it's what you can actually do with them. And that's where things get really interesting. So what can you actually do with 2 billion artificial neurons? Current AI models require massive GPU clusters consuming megawatts of power. Darwin Monkey is doing similar tasks with brain-like efficiency on 2,000 watts. But that's just the beginning. The system has been used to simulate the brains of various animals, zebrafish, mice, and macaque monkeys. We're talking about real brain simulation at biological scales. Darwin Monkey provides a high-fidelity, large-scale platform for modeling neural structures, offering a new experimental paradigm that could reduce reliance on live animal experiments. And then there's the robotics applications. Traditional AI requires constant internet connectivity. Your robot needs to phone home to the cloud every time it encounters something new. But neuromorphic systems? They can learn locally, adapt in real time, make decisions without any network connection. The edge computing implications are staggering. The low power consumption and compact design make neuromorphic systems ideally suited for deployment in power-constrained environments. We're talking about bringing real intelligence to devices that currently can barely run a calculator. While everyone's been worried about chip sanctions and semiconductor supply chains, China just built a completely different kind of computing stack. So where does this leave everyone else? Let's be honest about the current state of play. In traditional semiconductors, the US still holds significant advantages. TSMC, NVIDIA, Intel, AMD. These are still the companies defining the cutting edge. But neuromorphic computing? That's a different game entirely. Intel has Hollow Point, 1.15 billion neurons. Impressive for 2024. IBM has been working on neuromorphic systems for over a decade. European research programs, Japanese initiatives, academic labs worldwide, and China just leapfrogged all of them. Not by a little, by nearly 2 times in scale while using less power. Think about the geopolitical implications. The entire Darwin Monkey system is built with 100% Chinese technology and innovation, with no dependency on Western supply chains. No sanctions can stop this. No export controls can limit it. While Western policymakers have been focused on cutting off China's access to advanced GPU manufacturing, China was quietly building the successor technology. And now they're not just competing, they're ahead. So what comes next? If you follow the trajectory, you start to see a pattern. They're not just scaling randomly, they're following a roadmap. And if that roadmap continues, Darwin 4 could be approaching human brain scale. 100 billion neurons, the complexity of actual human cognition, running on the power budget of a light bulb. Current large language models are trapped by their power requirements. GPT-5, Claude, the big models everyone talks about. They live in data centers because they need industrial-scale electricity. But what if you could run similar intelligence on neuromorphic hardware? Suddenly, every smartphone could have GPT-level intelligence running locally. Every autonomous vehicle could make complex decisions without cloud connectivity. Every IoT device could learn and adapt in real time. And based on Darwin 3's performance, that if is looking more like when. China isn't just building better chips, they're building the foundation for technological independence in the post-silicon era. Here's what we learned today. While everyone's been obsessing over whether AI will pass the Turing test, China quietly solved a much more fundamental problem: how to build AI that doesn't consume the electrical output of a small country. Darwin 3 isn't just another chip. It represents a fundamental paradigm shift that positions China as a key leader in the next generation of AI hardware. Think about where we are right now. The current AI boom is built on an unsustainable foundation. Data centers consuming gigawatts of power, chips so expensive that only the biggest tech companies can afford to train state-of-the-art models. A computing paradigm that's racing toward physical limits. Neuromorphic computing offers a way out. Brain-like efficiency, local learning, adaptive intelligence that doesn't need the cloud. And China just demonstrated that this isn't some distant future technology. It's here, it works, and it's already surpassing Western alternatives. China's not just matching Western AI, they're doing it more efficiently, with less power, using indigenous technology that can't be sanctioned, export controlled, or supply chain disrupted. So the next time someone tells you that AI is going to transform everything, ask them this. What happens when AI doesn't need massive data centers to think? Because based on what we've seen from Darwin 3, that question isn't hypothetical anymore. If you found this deep dive into the future of computing valuable, smash that subscribe button and the notification bell. We'll be tracking every development in the neuromorphic race. And trust me, things are about to get very interesting. The real question isn't whether neuromorphic chips will change AI, it's whether we're ready for what they'll let us build.